Hello everyone, my name is Anggit Raksajati. In this video, I'm going to present you a preview of net positive suction head calculation in the fluid mechanics and particle course. When a pump is operating, there should not be any gas or vapor existence inside of the pump. Otherwise, it's going to be a problem, or it's usually called cavitation. So if we have a liquid over here and it's very close to the saturated condition or the vapor pressure, sometimes there is a risk that once it reaches the actual suction point of the pump, in this case is the point 3, some vapor will start to form, and that's going to cause a problem because of the erosion of the impeller diameter and the other moving parts of the pump, and it will damage the pump. So cavitation happens if P3 is less or equal than vapor pressure at specific or certain temperature. So again, be careful. We're talking about P3, the suction point of the pump, not the source point itself. So because of the difference in terms of the elevation or the friction loss between the source point to the suction point of the pump, it could cause some vaporization. So to calculate the net positive suction head, it can be calculated that at P3 it has to be higher than vapor pressure. So the energy calculation derived from the Bernoulli equation can be made comparing S, or the source, with 3, the suction point of the pump. And based on this equation, now we can get into this bottom equation that the delta pressure between source point with the P3 divided by the density and the gravity constant plus the elevation of the source minus the what is HFS, that's the head of friction in the suction part. So it only talks about the friction loss between source to suction point of the pump. So we're not talking about the friction loss between the discharge to the destination point. Again, only between the source to the suction point of the pump. And if P3 is identical with vapor pressure, that's when liquid starts to vaporize. So based on these two equations, now we can simplify that the NPSH has to be the delta pressure of source point minus the vapor pressure divided by the density and the gravity constant plus the elevation of the source. Actually, it can be plus or minus. I'll talk about it in the next slide. Minus the friction loss expressed in head between the source point to the P3, or the suction point of the pump. Or in more detail, I will talk that cavitation can be prevented when the NPSH available is bigger than the NPSH required. So there are two types of NPSH calculation. You just have to look into the position of the pump. In case A, the pump is below the tank 1 position, while in the case B, the pump is actually above the tank 1 position, and it actually make a difference in terms of the NPSH calculation. One can be expressed as positive, while the other case has to be expressed as negative. And the question is why? You just have to imagine that when you have a pump located below the tank, it actually helps the fluid to be flow between tank 1 to the pump because of the gravity. It's a liquid, so once you open the nozzle, the liquid will flow naturally from tank 1 to the pump. So because it's natural, it's not going to increase the risk of vaporization. So actually the elevation of the source is a plus because that increase the NPSH and that minimize the risk of cavitation. In the second case, where you have a pump located above tank 1, it actually already requires effort to suck the water from tank 1 to the pump. It will not flow based on gravity, so the pump will have to suck the water itself. And because of that, the pressure of 0.1 to P3 of the suction of the pump, which one will be greater? Of course, it's going to be P1. So at the exact suction point of the pump, there is a risk that the pressure is already lower than the source, and it will increase the risk of vaporization. That's why it's negative. Okay, so the question now, why do we have to even consider this second type where it's risk the cavitation? Well, you just have to imagine in your house, if you have groundwater from a reservoir or from a well, you can't put your pump 20 meters below the ground. It's just too much effort. So sometimes it's just much easier to put the pump at the ground level and let the pump to suck the water from the reservoir. As long as you choose the correct type of pump, it's okay. You don't have to worry about the cavitation. As long as you perform this calculation and make sure that at the suction point of the pump, it's still gonna be 100% liquid. Okay, so now we move on into the two type of NPSH, available versus required. So available NPSH, again, that's purely based on the calculation that we talked earlier, based on the differential of elevation, differential of pressure, etc. That's pure on hydrodynamics or the fluid mechanics calculation. While the required NPSH or NPSHR is determined by the manufacturer. So every time you buy a pump, just look at the data sheet or look at the brochure, what is the required NPSH by the pump. As long as you can prove that NPSH available is bigger than NPSH required, that means you can avoid cavitation. So if you look at this chart, at this point you don't have to worry. Why? Because the NPSH-A is still higher than the NPSH required. Once it intersects or even cross below the NPSH-R, then that's when you have to stop the pump operation because it will damage the pump. So how to get the NPSH-R? Again, it's determined by the manufacturer. If we look at the example explained in the previous video, I took an example from a pump shown in GPSA reference. Let's say we have 100 cubic meter per hour feed, and then we took into the secondary axis over here, the NPSH required is going to be 3 meter. So as long as we can prove that the available net positive suction head is bigger than 3 meter, it's going to be okay for our application. Okay, that's the end of this video. Thank you for listening.